Lachlan, Tanya. This year our team name is the Solar Synthesizers, and that's because we want to use solar energy to synthesize hydrogen gas. How do we aim to do that? Good question. There we go. All right, there's our first slide. How do we aim to do that? We want to engineer photosynthetic E. coli. For E. coli cells to be photosynthetic, they need to contain chlorophyll. For them to contain chlorophyll, they have to have the genes to synthesize chlorophyll. So to make that happen, we're taking chlorophyll synthesis genes from Chlamydomonas reinhardti. So green algae, you can see those, kind of cute. We're codon optimizing those genes for expression in E. coli. And yeah, we're going to put them in E. coli cells. Once we've got all that in place, we're going to introduce a hydrogenase into the system which can combine hydrogen ions and electrons to make hydrogen gas. So this is just a really generalized representation of photosynthesis, probably quite familiar to most people in this room, so I'm not going to belabor the point. But what's worth homing in on here is light energy in the form of photons coming into the photosystem 2 there. That energy is used to split water into hydrogen ions and electrons, which you can see at the bottom there. A hydrogenase enzyme is capable of combining them to form hydrogen gas, which is our desired end product. Chlorophyll synthesis, unfortunately, it's not just one gene involved. There's actually 13 of them there. They're all coloured in blue. So this is the pathway, stepwise, going from top to bottom to create chlorophyll A there. All these steps are the intermediates, and they're coloured according to what their visual colour is. And yeah, you can see all the genes in blue involved in each step. So if we can get all that happening and we can produce hydrogen gas, what is it actually good for? Essentially, hydrogen gas is a really good carbon neutral source of energy. When you combust hydrogen, you get energy and you get water. So that's obviously a lot better than fossil fuels where you get your carbon monoxide, carbon dioxide, etc. So eco-friendly, also renewable because all the energy is coming from the sun, which isn't scheduled to run out for another 5 billion years. So that's cool. Yeah, and I'll hand over to Tanya to talk about what we've been doing in the wet lab so far.
Yeah, sure.
Okay, so I had to talk about sort of the history of our project because it's ongoing, and we want to take it. So this is the same diagram that James showed us. So these 13 genes, we've organised them into 3 operons. So this is to aid the functionality because they work in groups. Now, last year's team, they managed to put all but 2 of the genes into Vibrix. And they did get some expression from the first operon. But as you can see, we've got a lot of work to do to complete. And we also did some sequencing of all these parts, and we found that one of them in the composite Vibrix was incorrect, so it's another thing for us to do to fix that. Now, this lovely big image here, this is, again, the 3 operons that we have, as well as photosystem 1. Now, this chlorophyll synthesis pathway, that's what we want to now complete this year. So we've been ongoing with this for a while, and we want to get everything from Chlamydomonas into E. coli and working. So of course we want to demonstrate to the iGEM judges that we have the functionality. So taking it from protoporphyrin 9, which is naturally occurring in E. coli, going through the pathway and get chlorophyll A at the end. And yeah, so a new component, so that's the thing, we want to complete the pathway and then start on something else, which is photosystem 1. So we've got a lot of these already designed, so we obviously have to get these synthesized and put into Vibrix. So some of the methods that we're using just broadly, so this of course is like the standard cloning that is common to get things into Vibrix with iGEM, and that's a little Pac-Man representation of Gibson assembly. So particularly we have the H gene, CHLH. It's roughly 4.5 kb, so it's massive. We've had that synthesized in 3G blocks and Gibson assembly to get them together. So in vitro assays, we'll be using those. So we need mass spec and SDS page to actually confirm that we've got the proteins there. But that's just having the protein and having it functional, of course, is different. So we need HPLC, as well as, sorry, my blank. But yeah, to actually confirm the function of the proteins. So yes, so just very broadly speaking, once we get the chlorophyll biosynthesis pathway, we actually get chlorophyll, then we want to move forward to photosystem 2. So that contains the oxygen evolution center, which is the bit that actually breaks water apart to get the oxygen and hydrogen or protons. So once we get that and we head towards down the path of photosystem 1, that's the academic basis of our project. So similar to the Yeast 2.0 project, we learn by creating and building. And of course the other part is when we add the hydrogenase, that's more towards the commercial applications. So we're just going to briefly talk about some of the dry lab stuff we've been doing. So of course we've been fundraising, so this is just 3 of the pages of the brochure that we created and sent out for fundraising. So lots of pretty pictures and students and everything. So we're all about the students and having fun in the sun and green, of course. So this is just a light glow with funny domain scenes. It doesn't have to make sense, it just has to look pretty, and then of course we're not actually up to the stage of building our wiki yet, but we're just working on the concept of, how do we want it to look? And look, I said this, we're going to do basically a bit of a mashup and compromise between these two, because they're actually wiki people. These are their concepts, so we're going to compromise and build something out of this. Okay, and now I hand over. Take it away.
Hi, so I'm Lachlan, so I'm just going to run very briefly through our human practices. So the first part of that is our implementation strategy. So I just wanted to start off by saying that globally, hydrogen is a $100 billion industry. Now, at the moment, it is very closely aligned with the petrochemical industry. However, moving into the 21st century, more and more innovation and investment is going into renewable technologies, such as hydrogen fuel production. Now, that's actually a picture there that shows an example of a bioreactor there. So moving forward, unfortunately that got cut off there. So should say product development. So essentially for us, our implementation strategy is about forming a two-way dialogue between industry and members of the community, so we can actually develop something that is hypothetically or potentially commercially viable. So in order to do that, I think it's important for us to identify the wants, the needs, and the fears of any potential industry participant that is interested in this sort of thing. Now, to explore that, we'd be exploring existing technology, so how competitive our proposal could be. Also to identify a target market. So at the moment, I've been looking extensively at, there's a lot of interest in solar capture technology, so transforming solar energy into a viable resource. And integration with laboratory work is really at the core of all this. So this diagram here shows pretty much a schematic of how our implementation strategy will fit into our lab work. So essentially for human practice, it will involve a lot of contact, well hopefully a lot of contact with people within the industry, but also the community side of things as well. So Lauren will actually introduce that briefly, our project there. Now, getting back to what I was saying, it's all about integration and feedback really. So moving forwards, I think it's going to be a continual process. There's going to be a lot of bumps along the road. We might not have a finished product at the end per se. However, it's about the process of actually moving towards that final blueprint. Now, moving on to something a little bit more exciting, Lauren's going to introduce So You Think You Can Synthesize.
So, backed by popular demand, So You Think You Can Synthesize Season 2 will surpass the views and the international recognition it got last year. Yes. Oh no. The trailer is here. My bad. Sorry, I copied the wrong file, so yeah, there you go. That's it, wherever it is. Do we have music?